The Compton effect. Even though photons are massless, they have momentum. The equation momentum equals mass times velocity for particles with mass cannot be used, since photons are massless. But Einstein's equation for the relativistic energy of a particle, this equation here, which you do not need to know, shows that a photon does have momentum. Since the mass of a photon is 0, this term goes away. We can take the square root of both sides, and we get the energy equals the momentum times the speed of light. So therefore, the momentum of a photon is its energy divided by 3 times 10 to the 8th meters per second. The energy of a photon is hf, E equals hf. So now we have these relationships that show that the momentum of a photon is directly proportional to its frequency, to the energy it has. This equation, in addition with the conservation of energy, can be used to explain the Compton effect. In 1923, Arthur Compton scattered X-rays off of a graphite surface and observed that the wavelength of the scattered X-rays increased, the Compton effect. Compton postulated that a photon, acting as a particle with an energy, E equals hf, and momentum, P equals h over lambda, collided with a stationary electron. As there are no external forces on the photon-electron system, the momentum and energy of the system are conserved. The momentum and energy of the electron increases, while both quantities decrease for the photon. Compton observed that the scattered photon had a longer wavelength than the incident photon. Photons with more energy or momentum have shorter wavelengths. Consider a photon colliding with a stationary electron. The gamma symbol is used for the photon. What happens when a photon collides with a stationary electron? Since momentum and energy are conserved in the collision, the momentum and energy that the photon loses is transferred to the electron. After the collision, the photon's momentum and energy decrease, and the wavelength of the scattered photon increases. As shown above, this is a simplified version, but a photon of blue light might become green light after a collision where it loses some momentum and energy. The incident photon rarely bounces straight back. The more realistic picture is shown below, and the amount of the wavelength shift depends on the angle that the scattered photon makes with the direction of the incident photon. Conservation of energy and momentum equations, using the relativistic versions as photons move at the speed of light, are used to derive the angular dependent Compton formula. You will not need to know this for the AP2 test. They could potentially give you this equation and ask you to use it, but it's not on the equation sheet.